Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we outlined how to prove particular statements of the form for all n p of n, where n ran over some set that satisfied this well-ordering property. And we showed that we could prove some statements of this form using a weak proof by induction. And recall that a weak proof by induction was done by first showing some base case, that was p of s was true, where s was the least element of this set that n is running over. And we also showed p of n implies p of n plus 1 is true for every n in s. And if we could show those two things, then it resulted that we showed that for all n in whatever my set was, p of n was true. And that was a weak proof by induction. And in this video what we're going to do is we're going to address a strong proof by induction, which differs ever so slightly from a weak proof by induction in the assumption that we normally make when kind of constructing our proof. And what do I mean by that? Well, normally when we construct a weak proof by induction, we make the assumption that p of n is true for some n in that set, or whatever the set that we're running over is. And we show that p of n plus 1 is necessarily true. So we show p of n implies p of n plus 1 is true. Now, for a strong proof by induction, we don't just assume that p of n is true for a single value and then show that it's true for the next value. We assume that it's true for some value and all values less than that value, and then show that the next one is true. So kind of tying back to this picture about dominoes, where before we said that we prove that we can topple over the first domino, and then if we pick up any other subsequent domino, we can topple over the next one. That's our weak proof by induction. A strong proof by induction, imagine kind of a line of dominoes, but the kind of dominoes are larger and larger and heavier as I kind of go along. Now, to knock over the next domino, it doesn't just require just the previous domino, it requires all the previous dominoes before to knock over the next domino. That is, we need to assume that it's true for all values before and show as a result of all those values before that the next one must be true as well. And that's this idea of a strong proof by induction. And the word strong is used is because it's a kind of stronger assumption. We're assuming that it's true for a lot more values than we would normally do for a weak proof by induction. So rather than kind of again waving my hands around and thinking about dominoes, let's look at the specific theorem of the principle of strong induction. So it has much a similar setup to we do have for weak proof by inductions, where we have statements of the form for all n in s p of n, where s is a well-ordered set. In this time we're going to take s as a subset of the integers, and it has a least element s, and p of n as always just has the domain of discourse in this well-ordered set. And we say that this thing is true if this kind of long compound proposition we've got here is true. And let's read what we're saying here. We're saying for every value of n in s and for all k in s such that this q of n comma k is true. Well, what is q n comma k? That says that that's all the values of k less than n. If all those values before n are true, and we can show that the next one is true, for every value of n, then it must have been true that p of n is true for every n in s. So this is much like what I said before. We now, rather than assuming that it's just true for the kind of one step and showing that it's true for the next step, we assume that it's true for all values up to some step and show that the next one is true. And that's effectively this strong proof by induction. Now, it's not immediately obvious that these things are the same. So we need to construct our proof, and we'll see how it results from our proof. So like before, because we've got an if statement here, we're saying if this long statement is true, it must be true that this next thing is true. We're going to prove, we're going to start by saying that the left-hand side is true. That is, for every n in s, and for all k in s satisfying this predicate qn comma k, pk implies pn is true. So let's start off here by substituting in a particular value for n, and we're going to substitute in the least value for n, that is n equals s. So when we get n equals s, we're just going to get the statement, exactly this statement above, but we're just put in n equals s. That is for all k in s, such that qs comma k, pk implies ps. We've just substituted n equals s, and we know that is true because we're assuming that it's true for every value of n, and s is inside the set capital S. Now, let's think about this restricted quantifier qs comma k. What's that saying? What values of k does that restrict us to? Well, that's all the values of k that are less than s. And k also has to be in this big set S. But because little s is the least element of s, there are no values of k that are less than s, because s is the least element. So it follows that there's just no values of k that satisfy that quantity, right? That satisfy that predicate. So, that we find the case then that, in other words, k here is the empty set, right? There are no values to check that satisfy this predicate that we've constructed. And therefore it follows that this thing is vacuously true. Why is it vacuously true? Because there are no values of k to check. So in other words, what we've got here now is above we've got some implication. We've constructed some implication and we say that that implication is true. And we've deduced that the left-hand side of that implication must be true. And by modus ponens, right, it sounds very much like we're constructing modus ponens again, the right-hand side must be true. So recall again, we've got P implies Q and P implies Q. In other words, if P implies Q is true and P is true, it follows that Q is true. And that's exactly what we've got here. So what's the thing on the right-hand side? That's P of S. In other words, we're concluding by modus ponens that P of S is true. So what should we do now? Let's look at maybe the next step. What happens if we put in n equals s plus 1? So if we put n equals s plus 1, kind of move this out of the way to make some room, it follows from the initial assumption that it's true for every n, that for all k and s, q of s plus 1 comma k, p of k implies p of s plus 1 is true. And that just follows right from our assumption that this thing is true for every n in s, and s plus 1 is indeed in this big set S. So, but now let's look at our restricted quantifier again, this q of s plus 1 comma k. That's saying all the values of k in this big set S such that k is less than s plus 1. Well, there's only one value that satisfies that, that's k equals s. So in other words, we're going to deduce again here that the left-hand side is true. Why is that true? That's going to be true because p of s is true. We've already deduced that. And hence by modus ponens, we conclude again that p of s plus 1 is true. So we've got, because the only value of k that satisfies this predicate is s, and we know that p of s is true by our previous step, we conclude once again by modus ponens that p of s plus 1 is true. And then we can continue this indefinitely, right? We're going to continue and show that p of s plus 2 is true, p of s plus 3 is true, and so on. And therefore it follows that for every n in s, p of n is true, which is what we wanted to show. So we finished our proof, and that's exactly what we mean by a principle of strong induction. So if we can show that this kind of long proposition above is true, then we will have shown that this for all n in s, p of n is true. So what's the difference here between a weak induction and a strong induction? Well, the first thing I said is that we're making a stronger assumption. We're assuming that p of n is true for all values up to some value, say k or so, and we're showing that it's true for k plus 1. And more importantly, or kind of interestingly here, you see that we didn't have to show a base case, right? Normally we show for a weak induction p of s is true explicitly. But in this situation, by just making that assumption, or if we can show that for all n in s, this argument held that for all k in s, qnk, pk implies pn is true, the base case was automatically shown, right? It was vacuously shown in our first step. We showed that if that thing is true, that p of s must also be true. So it's important to note here that a strong induction does not need a base case, right? That's what we've shown here. Or a proof by strong induction does not need a base case. But in reality, when we do specific examples, what we will see is in order to prove this long statement that we have above for a strong induction, it will rely on us showing some kind of specific cases for p of n. That is, we'll have to show p of n is true for some specific cases, and it'll normally be a finite number of cases. But depending on the particular statement, we don't know how many cases we have to show it for. It might be 2 values or 1 value or even 10 values, whatever it might be. It could be either way, it's a finite number of values, but we'll see that in order to construct that thing, in order to construct the proof of this kind of longer proposition that we have for a strong induction, it will rely on us proving some specific cases. And these are sometimes referred to as base cases in strong induction, but they're not in reality base cases. They're not base cases in the same way that we think of them in weak proof by induction, because they're different each time. And it just basically, these cases are kind of rely on or are needed in order to construct this proof of the kind of strong proof by induction. So let's see how this works in action with a specific strong proof by induction. So we're going to take a particular statement here which says for every n in M, it is the case that n to the power of 4 minus n squared is divisible by 12. So like before, we're going to write this in some sort of first order logic language, and we'll see that we can write that as for all n in n, p of n, where p of n is the predicate, n to the power of 4 minus n squared is divisible by 12. And we can see here that we are going to be able to use a proof by induction. We don't know which one, because we're using the set n here that we're running over, which is a well-ordered set. It satisfies our property and its least element is 1. But because this is a video on strong induction, and in fact proving this by weak induction is not so easy, instead it's easier to prove by a strong induction, let's try proving it by a strong induction. So recall that our strong induction step is that we show that let's assume that now p of n is true for some values of n running up to some other value k. So let's say p of n is true from 1 through k. Right, and then we're going to show that necessarily p of k plus 1 is true. So we're assuming this thing is true for a lot more values. That's our strong induction step. We're assuming that it's true all kind of for k and all values less than or equal to k, and we're going to show that it's true for the next step. Now notice here that I've got in my statement that k has to be greater than or equal to 6. And this is very important because if we didn't have k greater than or equal to 6, you'll see that my proof would not hold. And therefore what this is going to mean is at the end, if we can construct the proof here that if this thing is true and show that p of k plus 1 is necessarily true, at the end we will also have to show that p of n is true for 1 through 6, because we haven't, this thing only holds providing k is greater than or equal to 6. And therefore to finish the proof, we would also have to show that it's true for 1 through 6. And that's kind of what we mean by these base cases at the end. This proof relies on the fact that k is greater than or equal to 6. And because it relies on that, we will also have to show at the end that p of n is true for 1, 2, 3, 4, 5, and 6 in order to complete our full argument. So why do we need to have that it's k is greater than or equal to 6? Well, you'll see immediately that is the case because I'm going to do a change of variables. That is, I'm going to take s here to equal k minus 5. And notice here, right, if I took k to be less than or equal to 5, and I defined s to be k minus 5, that would take me outside the domain of discourse, because that would take me to some values less than or equal to 0, which is not inside the natural numbers. So I need to have that k is greater than or equal to 6 in order to do this change of variables. And this change of variables is going to be really useful because it's going to allow me to construct my proof. So what we're trying to do now, well, if we put in, first of all, we can say from our induction step or from our assumption that putting in s into kind of p of m, in other words, p of s, that thing must be divisible by 12. Why is that the case? Because we're assuming p of n is true for all values of n between 1 and k, and s is clearly between 1 and k because we're defining it as k minus 5. So it's inside that set. So it must be true that p of s is divisible by 12. That's what we're saying. In other words, s to the power of 4 minus s squared is equal to 12t for some t in n. And that's going to be useful for constructing now what p of k plus 1 is. So we want to now show that p of k plus 1 is indeed true. So we're going to put in p of k plus 1. And what does that give us? This gives us this thing here, which is k plus 1 to the power of 4 minus k plus 1 all squared. And we want to show that that thing is divisible by 12. And then we've done kind of our strong induction step. And then all that remains at the end is to show these final cases, namely that p of n is true for n equals 1, 2, 3, 4, 5, and 6. So I've done here my change of variables. So substitute in for s on the right-hand side. Now we get this s plus 6 to the power of 4 minus s plus 6 to the power of 2. And we just can expand that thing using a binomial expansion formula. So that results in this expression here. You can check that at home. It's fairly easy to expand the right-hand side, the squared expression, and expanding the expression to the power of 4, we just use your binomial expansion formula and you'll get this thing out here. But what's going to be useful now is we want to somehow use our assumption, our assumption that p of n is true for all these values of 1 through k. So let's see if we can factor out a term that looks like s to the power of 4 minus s squared. So doing that, we get an expression like this, and we automatically can say that s to the power of 4 minus s squared is divisible by 12, because that's part of our assumption. In other words, we can write that as 12t, like above, and we can factor out a factor of 12 on all the other pieces. So what have we shown here? We've shown that we can factor out this term 12, or we can factor out 12 into that expression, and therefore, this thing is divisible by 12. In other words, p of k plus 1 is divisible by 12. We've shown that if p of n is true for all values of 1 through k, where k was greater than or equal to 6, that p of k plus 1 will necessarily be true. And because we didn't make any assumptions on n, well, apart from the assumption that we made that k had to be greater than or equal to 6, it therefore holds at the moment that it's true for all values of n greater than 7, or greater than or equal to 7. And in order to complete the proof, in order to show that it's true for all values of n, we need to now kind of show that it is true for P1, P2, P3, P4, P5, and P6. So to conclude the proof, we just need to do that, show that it's true for those kind of values of 1 through 6. And that's fairly easy to show, right? You can do that at home, put this into your calculator, and see what you get out for each of those things. You find out that P1 is 0, P2 is 12, P3 is 72, P4 is 240, P5 is 600, and P6 is 1260. All of those are divisible by 12. Therefore, we've shown that P1 through P6 is divisible by 12. And our argument now holds that necessarily that for all n, where we've got P of n is less than some value k, or less than or equal to some value of k, P of k plus 1 is true. So we've shown that full strong induction statement, and therefore it follows that the whole thing is true for every single value of n in the naturals. So we've shown our strong proof by induction. So let's reiterate again here that even though we didn't have a specific base case, that when we were constructing this proof, it relied upon the fact that k was greater than or equal to 6. And therefore, even though all these implications held, it held as a result of k being greater than or equal to 6. And therefore, at the very end, we have to go back and check those values of 1 through 6 in order to complete the proof and show that it is true for all values of n in the naturals. So that's what we mean when we sometimes say proving base cases for strong inductions. But depending on the particular statement, the argument might rely on proving less cases or maybe more cases. I could use a strong induction, for example, to prove something about like an iterative sequence, but that would normally only rely on, say, proving 2 base cases. But there's not a specific way, or there's a specific number of base cases that we prove for a strong induction. The base cases arise as a consequence of us trying to prove this for all n statement. And we see that generally when we're trying to construct that argument will rely on us showing some specific statements are true, or the predicate is true for some specific values, and that depends on the particular statement. So that's where we're going to conclude the video now. And I really recommend that you read the notes on this topic, because this one was a kind of, you have to think very carefully about strong induction. And this is the final thing that we're going to do discussing on direct proofs. In fact, this is the kind of last video that we're going to talk about direct proofs. Inductions can be thought of examples of direct proofs. And in the next videos, we're going to talk about indirect proofs. And more specifically, we're going to talk about proofs by contradiction that you may have seen before, but we're going to construct them more rigorously. And we're also going to construct proofs by contrapositives, which are another form of indirect proof. So as always, I recommend you read the notes, especially for this video, and also try any problems in the module handbook related to strong induction. So thanks very much for watching, and I'll see you in the next video.